Yesterday in lesson 212, you found that the relationship between the height at which a ball is dropped and the height at which it bounces, or its rebound height, is a constant. What kind of graph was that represented by? Mary?
A linear graph.
A linear graph. And what was the slope of the line yesterday? Jane?
The rebound ratio we got.
The rebound ratio for your ball. All of you recorded your ball numbers yesterday. It'll be very important that you use the same bouncy ball today when we do our experiments. I'd like you to get into teams and start on problem 230 and then work your way through the lesson. I'll circulate around.
Okay. Does anyone want to start reading 230?
I will.
Okay.
230. Consider the work you did in lesson 212, in which you found a rebound ratio. A. What was the rebound ratio for the ball your team used?
It was 0.73.
Yeah, that's what we got yesterday. And then B. What did the height you dropped the ball from affect? Did the height you dropped the ball from affect its ratio? No, it was the same every time because it was the same ball. C. If you were to use the same ball again and drop it from any height, could you predict its rebound height? Explain.
Yeah, you could, because you could use the ratio that we found yesterday.
You
Right.
can
Figure
times
out
the rebound
the-
ratio by the drop height to equal the rebound height.
Okay. Imagine that you dropped the ball you used in problem 221 from a height of 200 centimeters, but this time you let it bounce repeatedly. A. As a team, discuss the situation, then sketch a picture showing what this situation would look like. Your sketch should show a minimum of 6 bounces after you release the ball.
Does your guys' kind of look like that?
Yeah.
Yeah.
Okay.
B. Predict your ball's rebound height after each successive bounce if its starting height is 200 centimeters. Create a table with these predicted heights.
How do you do that?
Well, because every bounce is going to have the same ratio because it's just the same ball. So wouldn't you take the rebound height from the first one and make that the new starting height and just keep going?
Oh, and just multiply that by 0.73 every time?
Yeah.
All right. This one?
D. Graph your predicted rebound heights.
If you guys want to do it on your calculator, I'll do it on my paper and see if it's the same.
Okay. Yeah, this is what I got on the calculator.
So with me.
E. Should the points on your graph be connected? How can you tell?
I don't think they should be connected
Yeah, me neither.
because you can't have like a 0.5 bounce.
And if they were connected, it would have one,
Yeah.
right?
So-
Okay.
Students drop the ball to test their predictions.
146 again. 110, 75, 62, 51, 40, and 32. The problem was is to compare them with our old results. So I still have my graph on my calculator, and then we can graph these and see how they compare.
Yeah, I have the new ones.
Okay. The numbers from the old one are really close. On the
Yeah, they
first
are.
bounce, it was the same.
Are you comparing the bounces to your predictions?
Yeah.
Yeah.
On the second bounce, we were off by 2. On the third bounce, we were off by 3. On the fourth bounce, we were off about 4. And then on the fifth bounce, we were off by 10. And then the next one, we were off by 10 again. But that's because the difference keeps getting bigger because we keep starting it from a new place.
Yeah.
Great explanation. Great job there. It's time for us to have a discussion. Can I have the ball here? May I use your calculator that shows both pieces of data? Great. Thank you. Now, all of you have a graph that seems to look similar to this, either on your paper or in your graphing calculators. And some of you have multiple sets of data. This team ran it twice. Did your results match your predictions?
At first they matched our predictions, but then we noticed as we got farther and farther with the bounces, there was a greater difference because if it was just a couple off from the first time, it would be a couple off from the next time, and it would just keep adding up.
Okay. Today was an example of a graph or a function we call exponential decay. And so I have a question that I'd like you to discuss in your teams for closure. And the question is, do you think the ball will ever stop bouncing? Attention, I'd like to hear the results of your team conversations, and I'd like other teams to hear them in case you don't all have the same conclusions. You understood the prompt was, will it ever reach a height of 0? Will the ball stop bouncing? Who's got some ideas, or can you share out reporters, report what your team had to say? Okay, Nick?
I think at one point the ball is just going to run out of energy, or it's just going to run out of bounces. So I think it's just going to like bounce infinitesimally small for a long, long time, and then at one point it's just going to run out of bounce.
Okay, so you say it will reach 0 down here. Mary?
Well, my team decided that according to our equation, and we think that mathematically, in theory, it won't ever stop bouncing, but we know that a ball stops bouncing eventually.